All right, so consider the process ABCA. Oh, okay, let's see, A to B. So this is an isothermal expansion, right? And then there's an isochoric heating, and then an isobaric compression, and then we're back to A. Okay, it's 1.45 moles. Show that the process AB is isothermal. Okay, so isothermal means that the temperature is constant. Okay, so what this means is that if we use the combined gas law, that means that PV equals PV, right? So what we can do, if you look at this, there's a few places where we go through grid lines here, okay? And you could try to read off, these other things, but we definitely have 3 places there that seem to beg for us to calculate things, right? So let's look at this. This is 12 and 3. Do you see that? And notice that it's times 10 to the 5th, and this is times 10 to the minus 3rd. But that doesn't really matter. If P times V equals P times V, it does in any unit, right? Okay, so 12 times 3 is 36. Let's look at this guy here. That's 6 times 6. I'll call this point D or something like that, or A prime or something like that, right? And then look at this guy. This is 4 times 9. 4 times 9 is 36. So yes, okay. Okay. You could also calculate the temperature here and the temperature there, and show that these endpoints have the same temperature. But anyway, so 2 ways to show that something's an isothermal process. One is to just do a bunch of PV calculations and show that they're all the same. Okay. The other one is to actually calculate the temperature at a bunch of points. You could do that too. So they say it's 1.45 moles. We know that PV is nRT. So therefore, T is going to be PV over nR. So at A, the pressure at A is 12 times 10 to the 5th. The volume at A is 3 times 10 to the minus 3rd. N is 1.45. And R is 8.31. So this is at point A. So let's do that. 12 E5 times 3 E minus 3 divided by 1.45 divided by 8.31 is 298.767. Or 299 kelvins, right? So let's look at B. Now, of course, this is isothermal, right? So it should be the same temperature, but let's check it. All right, so let's see. B is, the pressure is 4 times 10 to the 5th. The volume, though, is a whopping 9 E minus 3. So, and then that's divided by 1.45 and 8.31. And of course, you can see that the numerators are identical here, so we're going to get the same answer, but that's okay. Let's do this. Now, I'm sufficiently lazy that I'm just editing my previous thing. Let's see. 9, and not 12, but 4. Hey, look at that. That gives us 298.767 kelvins. And let's go C. C is going to be different, okay? C is going to be different. Now, there's 2 ways to get the temperature at C. We could just do the ideal gas law, but I'll bet that A to C, C is 9. It's the same pressure as A, but it's 3 times the volume, so it's going to be 3 times the pressure. Or sorry, it's 3 times the temperature. Okay, so it's going to be 3 times 299. Okay, or whatever, 3 times this number. So that's one way to do it. But let's go ahead and just do the ideal gas law. Okay, so C is 12 E5. That's our pressure, right? And our volume is 9 E9, or sorry, 9e minus 3. 99 is a fundamental constant. Well, some kind of a constant. And 8.31. All right. Okay, so 12e5 times 9 divided by 1.45 divided by 8.31, which is 896.3. All right. I'm going to store that in C. Whoops. Alpha C. And I'm going to store the 298 guy in alpha A. Okay, so now let me just show you something, right? If you take this number and go times 3, you get exactly the same number, okay? So you could use just, eyeballing it, right? This is 3, this is 6, this is 9. Or you can use the ideal gas law. Those are two ways to do the same thing.